Hello everybody, my name is Nicolas Trangez. I work as an architect at Scality OpenStack architect. Scality is a company which creates storage solutions. We create petabyte scale software-defined object and file storage, which is fully scale out, so it linearly scales with the number of servers you deploy. And it is fully hardware agnostic, so you can run it on any server, whether this is high-end enterprise or low-end consumer-grade servers. The core of our software is called Ring, and this provides several methods to store your software safely, store your data safely, using replication or erasure coding, which we call ARC. And you can work with your data using a couple of connectors. We have some of those. One of them, the most performant one, is using plain HTTP. It's called sproxd, and we'll get back to that one later. We have some connectors for S3 and CDMI at the object level. We have Fuse, NFS, and SMB or CIFS for file systems. And then we have several application-specific connectors, for example, for messaging use cases, including email. This is a small overview of how the thing works. So we have one storage solution at the very bottom where your standard x86 servers run. We have a layer on top of that one, and then the application-specific connectors on top. Since about 1 year, even a bit more, Scality is involved with OpenStack. We have a fully dedicated engineering team, and we integrate with all the existing OpenStack storage projects, including Cinder since the Grizzly release, which is fully in tree. We have, since very recently, a Glance connector, a Glance store, which is for now out of tree, but we'll try to get it in tree as well. And we integrate with Swift, where this talk will be about. We are looking into Manila, the shared file system service, and that will be for the second half of this year. One of our strengths is how we can eliminate multiple storage silos. We can handle most of the OpenStack storage workloads, about 80% of them, especially obviously the object storage, and it scales up to petabytes and beyond. One important thing is the company really encourages us to work on other OpenStack projects as well. We really get time to do so. It is not only on the storage solutions. So this is an overview of where we integrate with Swift, with Glance, with Cinder, but I guess most of you know that system. Here's how we integrate with Swift specifically. So there is a custom replication running on top of Swift, and we reuse most of the Swift infrastructure. So we are fully compatible with the Swift APIs and with Swift middleware, etc. We only replace the DiskFile inside the Swift object servers, which then talk to sproxd, which is our HTTP connector, which then stores your data safely into Ring. So this talk is about Swift storage policies and how you can use those. Storage policies allow an administrator to define certain classes of storage with different levels of performance, different SLAs, different pricing models, most likely. And a tenant, so a user of the Swift service, can assign such policy to a container at creation time of the container. Objects are then, when put inside a container, stored according to this policy. In the upstream Swift, this would be a replication count using spindles or SSDs or using erasure coding since they're kilo release. In Scality, we map this to a set of sproxds with different configurations. So we'll go into that into more detail later on. Here are some use cases of these storage policies. So it's very important to know that we reuse Swift, and Swift enables us to provide certain services which we can or we don't do in the plain sproxd access to the data. One use case is splitting up between performance and cost. So you can do replication, which is high performant but pretty costly because you have a multiplier overhead. Or you can use erasure coding, where the storage is more cheap. You use less storage, but the performance goes down in latency, time to first byte. Replication allows for very efficient random access. Erasure coding is mostly for streaming workloads. You can split between spindles or SSDs, as mentioned before. And depending on the application, you might want to move your data from one container, from one storage policy to another one over time, just to reduce cost when performance is less important. A second use case would be geo-distributed storage, which is highly impacted by network latencies, as we all know. There we want to keep locality operations as local as possible. We don't want to go across the ocean if the data is also available locally. And so certain storage policies can take these locations into account, and we make sure that operations happen as locally as possible. This also is of use when certain constraints are put in place, like for example with privacy laws. We all know in Europe you need to store certain data within a certain country, for example. And so storage policies allow to specify and ensure these, the placement of your data complies to these laws. There are two ways of doing geo-replicated storage. You can have a single storage system which crosses multiple data centers, multiple sites, but this requires relatively low latencies. The Scality implementation of this is location aware, so it provides a certain level of disaster recovery when a full site goes down. And we ensure, as mentioned before, that our Swift connector will talk to close-by connectors as much as possible. So you will not go all the way. If you're in Paris, we are located in Paris, among other places. If you're in Paris, you don't want to head your request to San Francisco, which then goes back to Paris to retrieve some data, then goes back to San Francisco to send it back to you. That makes no sense. There is a second geo-replicated setup, which is active-passive, where you store your data in a single data center or a cluster of multiple data centers, and then asynchronously offload it to a second data center. This provides full disaster recovery over a full site. This allows for use cases like ensuring that data is stored as local to its use as possible. For example, if you produce data in Paris, but it should be available in San Francisco and New York, you might want to replicate it to those both locations. It's a bit like a content distribution network. This works really well with immutable objects because of the replication and the asynchronousness, the fact that this is asynchronous. One very concrete use case here is a movie production studio who works across the world, but for certain reasons, most likely business reasons, all the data must end up in LA or wherever the studio is located. This can be done continuously or only once in a while, except for example at night. And here it is important due to the inconsistencies between the different clusters that you only provide create, update, and destroy operations at the source of your data, and then you read from any other one where the data is distributed to. So we ensure this inside our connector. The implementation, as mentioned before, reuses Swift and everything Swift supports as much as possible. We also reused what we already announced back in Paris in our Swift connector. We added some things like HTTP connection pooling and then a failure detector to make sure that we will not rely on services, backend services that are no longer available. And we made sure that the whole configuration of this, which can become pretty big, it can be done in only a single file and can be shared across every single one of your servers. There is no server-specific configuration required, except if you want to optimize for locality, then a server must know somehow where it is located, so it can sort the other endpoints accordingly. On the right, you can see how this configuration looks like. So we have 3 rings defined, 4 rings defined, 2 in Paris, 1 using replication, triple replication, but the name really doesn't have any significance. And then 1 in San Francisco, 1 in New York, both using erasure coding, and 3 storage policies, where in the first one, all data should be written to New York and is then lazily offloaded towards San Francisco and Paris. There is a second one where you write to Paris, and this will be synchronized to New York. And in the third one, we only write and read from Paris. That is about all there is to say about our support for storage policies and how these are used by our customers. A little bit more about Scality. We were funded in 2009. We have over 70 deployments, real-world deployments. We have our headquarters in San Francisco. We have offices in Washington, and we have a very new lab in Boston. We have our R&D in Paris. We have an office in Tokyo and Singapore. We're currently about 130, 140 employees, but this is increasing really quickly. I joined myself 7 months ago, and ever since then, I've seen lots of new colleagues. And we see an immense growth in our sales. If you are interested in us, please, we're hiring. That's it. Any questions? Okay.